This presentation is part of a lecture series on multi-resolution signal and geometry processing by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series, as well as the corresponding textbook, can be downloaded from the website whose URL is given on this slide, in particular this URL here. In this next section of the lecture slides, we're going to look at polygon meshes in CGAL. The CGAL library provides a template class called polyhedron 3, and this class represents a polyhedral surface, or in particular a polygon mesh, which consists of vertices, edges, and facets, and some incidence relationship amongst them. Each edge is represented by a pair of half edges, and a half edge is just a directed edge. So each edge is represented by a pair of directed edges that are oriented in opposite directions along the edge. The declaration for the polyhedron 3 class is as shown on the slide here. The first parameter for the template is a type, which is the type of the geometry kernel that's used in conjunction with the polyhedron 3 class. So again, a geometry kernel in CGAL is the thing that specifies how points are represented, whether Cartesian coordinates are used or homogeneous coordinates, and also the numeric type used to represent the coordinate values for Cartesian coordinates or homogeneous coordinates, and so on. Also, the kernel provides basic geometric operations and predicates. A couple of examples of geometry kernels are Cartesian double or filtered kernel Cartesian double, and there's many others as well, of course. The next template parameter is polyhedron items. And polyhedron items is used to specify the data types that represent vertices and facets. You can use the default value that's provided here, which will provide a certain base level of functionality in terms of what members are provided by the Vertex class and Facet class that are used by the polyhedron 3 class. However, you might want to add some additional members to the class, maybe some additional data members to store extra information in vertices or to store extra information in facets. And you can do this by overriding this default and providing your own classes. In many cases, however, the default will suffice, but sometimes you'll need to override the default. The next parameter is half-edge ds. Half-edge ds specifies the half-edge data structure used for representing the polygon mesh. Again, it's a half-edge based data structure that's used by polyhedron 3. And the next parameter is alloc, which is just an allocator, similar to the sort of allocators that you have in the standard template library, or part of the standard library that are used for container classes. The defaults for half-edge ds and alloc are most likely going to suffice, except in maybe much more advanced usages. The polyhedron 3 class has a number of type members, which we're going to look at now. There's some very basic types, for example, vertex, which is the type that's used to represent vertices in the mesh, half-edge, which is the type used to represent half-edges in the mesh, facet, which is the type used to represent facets or faces in the mesh, and point 3, which is used to represent the coordinates of points in the mesh. It's basically a point in 3 dimensions. There's also a number of handle types. Handles are essentially very similar to pointers in terms of their functionality. They're used to refer to different components within the mesh. And handles come in constant, mutable varieties. So for example, we have vertex const handle. This is a handle to a vertex. It's similar to a pointer to a vertex. It refers to some vertex. And this particular type, the word const that appears in the type is indicating that this is a const handle. In other words, it's a handle that you cannot use to modify the vertex that the handle refers to. It's similar to a pointer to something that's const. And then we have a vertex handle. This is the mutable version of the handle. In other words, it's a handle that you're allowed to modify the thing that the handle refers to. It's like a pointer to something that's not const. And then we have a similar sort of thing for both half-edges and facets. So we have a const and non-const handle for half-edges and a const and non-const handle for facets. Again, facet and face are basically synonymous. Next, we have a number of iterator types in the polyhedron 3 class. And these iterators allow us, for example, to iterate over vertices in the mesh, or half-edges in the mesh, or faces in the mesh, or edges in the mesh. And each of these iterator types comes in two flavors. There's the const flavor and the mutable flavor. So for example, vertex const iterator is an iterator that you're not allowed to modify the thing that the iterator refers to. You can't modify the vertex that the iterator refers to. Then we have the mutable version, which doesn't have the word const in it. And this is with a vertex iterator, you're allowed to modify the vertex that the iterator refers to. And again, iterators are used to iterate over, in this case, vertices in the mesh, these two iterator types. Then we have a similar pair of types for half-edges, the const version and then the mutable version. A similar thing for facets, in other words, faces in the mesh. We have a const version and a mutable version. And then for edges, we have a const iterator and then a mutable iterator as well. Although the name is a little bit misleading because edges are not actually explicitly represented in the polyhedron 3 class. What the edge iterator actually does is it iterates over every second half-edge. Or maybe more specifically, each edge has two half-edges associated with it. And if you use the edge iterator, what will happen is as you iterate over all of the edges, you will visit one of the two half-edges of each edge once. So it's a little bit misleading. There are no edges really to iterate over per se. Instead, you'll be actually iterating over half-edges, but you only visit one half-edge from each edge. Finally, in the polyhedron 3 class, we have a number of circulator types. Just like in the case of handles and iterators, circulator types come in two forms, const and mutable. Const circulators are not permitted to modify the object to which they refer, whereas mutable circulators are allowed to modify the object to which they refer. And there are essentially two kinds of circulators. We have what are called half-edge around vertex circulators, and these are the first two types that appear in the table. So what a half-edge around vertex circulator does, it allows you to circulate or iterate over half-edges that are incident on a particular vertex in clockwise order. The order is important because you may care about the order in which the half-edges are visited in certain cases. So the order is clockwise. The other kind of circulator is represented by the last two types in this table, which is a half-edge around facet circulator. And what a half-edge around facet circulator does is it circulates or iterates over all of the half-edges that are incident on a particular facet in counterclockwise order. Again, be careful about the order. It's counterclockwise in this case. And notice that some circulators visit elements in clockwise order and some visit in counterclockwise order. So it's important to be careful about the order. The polyhedron 3 class has a number of function members, which I'm going to introduce now. There's some function members that relate to size. So for example, there's a member function called size of vertices, which returns the number of vertices in the mesh. There's another function called size of half-edges that returns the number of half-edges in the mesh. And then size of facets returns the number of facets or faces in the mesh. There's also a number of functions that relate to iterators. We have the kind of common pattern that you have with a lot of the container classes in the standard library. There's a begin function that returns the iterator for the first thing, and then an end function which returns the corresponding past the end iterator for that same kind of thing. But in the case of a polyhedron 3 class, essentially what we have is a container with like multiple types of things in it. We have a container that has a bunch of vertices, a bunch of half-edges, a bunch of facets, and a bunch of edges. So we have a begin and end for each one of these things. So there's a function called vertices begin, which returns an iterator for the first vertex in the mesh, and then vertices end, which returns the past the end iterator for the vertices in the mesh. And then we have a half-edges begin and half-edges end member functions. Half-edges begin returns an iterator to the first half-edge in the mesh. Half-edges end returns the past the end half-edge iterator. And then similarly for facets begin and end, except this is for facets. You get an iterator which refers to the first facet in the mesh, and then facets end returns the past the end facet iterator. And similarly for edges begin and edges end. Although in the case of edges begin and edges end, again, this is a little bit misleading the name. There are no edges that are explicitly represented in the polyhedron 3 class. Edges are referred to by their corresponding half-edges. So edges begin and edges end return edge iterators, but the edge iterators are really referring to half-edges. It's just that when you're using an edge iterator, you only visit half of the half-edges. You only visit one half-edge for each edge. The polyhedron 3 class also provides a number of function members that are combinatorial predicates. predicates are typically things that return true or false, and they're used to test some condition. The first of these predicates is closed. This function tests if the mesh is closed. In other words, it has no boundaries. So this function will return true if there are no border edges for the mesh. In other words, the mesh has no boundary. It's a closed surface. The next function is pure triangle. It's a predicate that's used to test whether or not the mesh is a triangle mesh. In other words, it tests if all of the facets are triangles, and it returns true if all facets are triangles and false otherwise. And then the last predicate is pure quad. It tests whether the mesh is a quadrilateral mesh. In other words, it checks if all the facets are quadrilaterals. If they are, it returns true, otherwise it returns false. The last group of member functions for the polyhedron 3 class relate to border edges. In some geometric algorithms, it's convenient to group the border edges together and then group the non-border edges together. This is because often in geometric algorithms, you'll want to treat the border and non-border cases in different ways. So for this reason, the polyhedron 3 class provides an operation known as border normalization. And what border normalization does is it reorders the half edges for the polyhedron 3 object so that half edges for non-border edges come before the half edges for border edges. And the particular function normalize border, what this does is this performs this border normalization process. So after this function normalize border is called, the half edges will be sorted so that all of the half edges that are associated with non-border edges come first, followed by all of the half edges that are associated with border edges. So if, for example, you iterate over all the half edges, you'll see all of the half edges for non-border edges before you visit half edges for border edges. The function normalize border is valid, tests to see whether or not the border is normalized, and it just returns true or false. True if the border is normalized, false otherwise. The remaining functions in this table, size of border half edges, size of border edges, border half edges begin, and border half edges, border edges begin. These four functions only can be called if the border is currently normalized. And this is very important. Otherwise, if you call one of these four functions, size of border half edges, size of border edges, border half edges begin, and the border isn't normalized, you don't really know what's going to happen, probably nothing good. So assuming that the border is normalized, what do each of these four functions do? Size of border half edges returns the number of border half edges in the mesh. Size of border edges returns the number of border edges. Border half edge begin returns that half edge iterator that's the start of the border edges. And border edges begin returns an edge iterator that corresponds to the start of the border edges. As we saw earlier, one of the type members of the polyhedron 3 class is the facet type, and now we're going to look at this facet type in more detail. So the facet type represents a facet or face in a polygon mesh, and the actual class type to which facet corresponds depends on the choice of the polyhedron items template parameter used for the polyhedron 3 class. If you recall, when we talked about the polyhedron 3 class, there was a template parameter called polyhedron items. And effectively what this template parameter does is it selects the particular type that's used to represent a facet, the particular type that's used to represent a vertex, and the particular type that's used to represent a half edge for the particular polyhedron 3 class that we're using. And depending on what specific type facet refers to, the level of functionality that's offered by the facet class can differ. In other words, you might have different function members available to you. The facet class can contain a number of optional items. The first is a plane equation. In other words, it may contain the equation of a plane that contains the face, assuming that the face is planar. Also, the facet class may contain a handle for a half edge that's incident on the facet. Some of the member functions in the facet class provide access to a half edge around facet circulator. This is a circulator that allows you to iterate around all of the half edges that are incident on a particular facet. And the half edge around facet circulator may be either forward or bidirectional. If it's forward, meaning that you can only apply the increment operator to the circulator, you can't do a decrement operation. And bidirectional, meaning both the increment and decrement operations are supported by the circulator type. Some of the member functions provided by the Facet class are listed on this slide. The first group of functions listed in the top table on the slide is only available if the facet contains a plane equation, which is an optional item. In this case, we have a member function called plane that can be used to obtain the plane equation for the face. The second group of functions listed in the bottom table on the slide is only available if the facet contains a handle for an incident half-edge, which is another optional item. In this case, we have the following functions. A function called Halfedge that gets a handle for one of the half-edges incident on the facet. Facet begin, which gets a half-edge around facet circulator for the facet, and this can be used to circulate or iterate over half-edges that are incident on the facet in counterclockwise order. The function set half-edge, which can be used to set the handle for a half-edge that's incident on the facet. Facet degree, which gets the degree of the facet, in other words, the number of sides on the face or facet. Is triangle, which returns true or false, indicating whether or not the facet is a triangle. It returns true if the facet has three sides, in other words, it's a triangle, and false otherwise. And is quad tests whether the facet is a quadrilateral. In the case that the facet is a quadrilateral, it returns true, otherwise it returns false. As we saw earlier, one of the type members of the polyhedron 3 class is the vertex type. Now we're going to look at this vertex type in more detail. So the vertex type represents a vertex in the polygon mesh. The actual class type to which vertex corresponds depends on the particular choice of the polyhedron items template parameter for the polyhedron 3 class. Earlier when we talked about the polyhedron 3 class, if you recall, there was a template parameter called polyhedron items. And essentially what this template parameter does is it selects the specific type that's used to represent a vertex, a facet, and a half-edge in the mesh. Depending on the actual class type to which vertex refers, the level of functionality that's offered by the vertex class can differ. In other words, the member functions that are available to you can differ depending on the specific type that vertex refers to. The vertex class can contain some optional items. In particular, it can contain a point, which is the position of the vertex in space, and also a handle for a half-edge that's incident on the vertex. Some of the member functions in the vertex class provide access to a half-edge around vertex circulator. This is a circulator that allows you to iterate over the half-edges that are incident on a particular vertex. And the half-edge around vertex circulator may either be a forward circulator or bidirectional circulator. A forward circulator being a circulator for which the increment operation is defined but not the decrement operation. In other words, you can only circulate in one direction. A bidirectional circulator is a circulator where both the increment and decrement operations are defined, so you can circulate over things in both the forward and backward direction. Some of the member functions provided by the vertex class are listed on this slide. The first group of functions listed in the top table on the slide is only available if the vertex contains a point corresponding to the vertex position in space, which is an optional item. In this case, we have a function called point, which can be used to get the point associated with the vertex. In other words, obtain the point in space that's associated with the vertex. The second group of functions listed in the bottom table on the slide is only available if the vertex contains a handle for an incident half-edge, which is another optional item. In this case, we have the following functions. We have a function called half-edge that gets a handle for one of the half-edges incident on the vertex. Vertex begin, which provides gets a half-edge around vertex circulator. And this circulator can be used to circulate or iterate over half-edges that are incident on the vertex in clockwise order. The function set half-edge sets the handle for a half-edge that's incident on the vertex. Vertex degree, which gets the valence of the vertex, is bivalent, which checks to see if the vertex has valence 2. It returns true if the vertex has valence 2 and false otherwise. And the function is trivalent, which returns true if the vertex has valence 3 and false otherwise. So it checks if the vertex is trivalent. As we saw earlier, one of the type members of the polyhedron 3 class is the half-edge type. So the half-edge type represents a half-edge in our polygon mesh. Again, the polyhedron 3 class uses a half-edge based representation. The actual class type to which half-edge corresponds depends on the choice of the polyhedron items template parameter for the polyhedron 3 class. If you remember polyhedron 3 class, when we talked about it earlier, it's a template class. One of the template parameters was called polyhedron items. And this polyhedron items template parameter, essentially what it does is it specifies the particular type that's used to represent a half edge, a vertex, and a facet in the mesh. So depending on the actual class type to which half edge refers, the level of functionality that's offered by the half edge class can differ. In other words, you may have different member functions available depending on the specific type that half edge actually refers to. Each half edge is directly associated with one vertex and one facet, which are referred to as the incident vertex and the incident facet respectively. The incident vertex is the vertex at the terminal end of the half edge. In other words, in terms of this picture here, we have a half edge. It's directed from this endpoint to this endpoint here. And the vertex at the terminal endpoint is this vertex here, as opposed to the originating endpoint, which would be this vertex here. The incident facet is the facet to the left of the half edge. In other words, if you imagine that you're standing on this page here and you're facing in the direction that this half edge is pointing, the face that will be on your left is going to be this one here. So this is the incident facet. Amongst other things, a half edge contains a handle for the next half edge around the incident facet in the counterclockwise direction, and a handle for the opposite half edge. In other words, the half edge that's associated with the same edge but oriented in the opposite direction. And together, these two handles allow for efficient iteration around half edges that are incident on a facet, particularly in the counterclockwise direction, and half edges that are incident on a vertex, particularly in the clockwise direction. A half edge may also include an additional handle, which is for the previous half edge around the incident facet in the counterclockwise direction. And by adding this extra handle, this allows for efficient iteration around half edges that are incident on a facet in both directions, with emphasis on the word both, and also allows efficient iteration around half edges that are incident on a vertex, again in both directions, with emphasis on the word both. A half edge may also contain some additional items, namely a handle for an incident vertex and a handle for the incident facet. Lastly, if the half edge class provides a prev member function, this stands for previous, the half edge around vertex and half edge around facet circulators will be bidirectional. In other words, they'll support both the increment and decrement operation. Otherwise, they'll be forward circulators only. In other words, they only support the increment operation, not the decrement operation. On this slide and the next few slides, we're going to examine some of the member functions provided by the half edge class. So the first group of functions here are for adjacency queries, or for extracting adjacency information from a mesh. The first function, opposite, gets the opposite half edge. In other words, it gets the half edge that's associated with the same edge but oriented in the opposite direction. The next member function gets the next half edge that's incident on the same facet in the counterclockwise ordering. Prev, which stands for previous, gets the previous half edge incident on the same facet in the counterclockwise ordering. And then next on vertex and prev on vertex, where prev stands for previous, these two functions get the next half edge and previous half edge incident on the same vertex in clockwise order. Then the next bunch of functions are for circulators. The first function, vertex begin, gets a half edge around vertex circulator for the incident vertex. And remember, these circulators circulate in clockwise order. And then facet begin gets a half edge around facet circulator for the incident facet. And remember, this type of circulator iterates in the counterclockwise order. The next group of member functions for the half edge class relate to border queries. The first function, isBorder, tests if a half edge is a border half edge. Again, a half edge is a border half edge if it has no left face, because the left face is missing due to the fact that the half edge belongs to an edge which is on the border of the mesh. The function isBorderEdge tests whether a half edge belongs to an edge that's on the border of the mesh. In other words, the half edge either has its left face missing or its right face missing due to the fact that it belongs to an edge that's on the border of the mesh. The next group of functions are used for querying the valence of vertices in the mesh. So vertex degree returns the valence of the incident vertex. Is bivalent is a predicate, it returns true or false. indicating whether or not a vertex has a valence of 2. It returns true if the valence is 2 and false otherwise. A predicate called is trivalent that returns true if the incident vertex has valence 3 and false otherwise. So it's testing if the vertex has valence 3. Then we have some functions which relate to facet degree queries. In other words, checking to see how many sides a face has or facet has. The function facet degree gets the degree of the incident facet. In other words, returns the number of sides that the facet has. Is triangle is a predicate that returns true if the incident facet is a triangle. In other words, it has 3 sides, or degree 3. Is quad is a predicate that returns true if the incident facet is a quadrilateral. In other words, it has 4 sides. Lastly, on this slide, we have some member functions for the Halfedge class that may or may not be available depending on what functionality is supported by the Halfedge class. The first group of functions, or it's really just one function called Vertex, this category corresponds to operations that are available if the Halfedge stores a handle for its incident vertex. In this case, there's a member function called Vertex that gets this handle. In other words, it gets the handle for the incident vertex of the Halfedge. The next group of functions, for which there's only one function called Facet, are functions that are available if the Halfedge stores a handle for its incident facet. So if such a handle is stored, there's a function called Facet that returns this handle. In other words, it gets the handle for the incident facet of the Halfedge. At this point, it's worthwhile to consider a simple example illustrating the use of several of the adjacency query member functions of the Halfedge class. In the figure on the slide, we have a polygon mesh consisting of several triangle faces. One half-edge of interest has been labeled as H in this particular figure, this half-edge here, and then several other neighboring mesh elements are labeled with an expression by which they could be referenced. So for example, if we wanted to refer to this particular half-edge here, we could reference it by using an expression that looked like this in our code. In other words, by applying the opposite member function to the half-edge H. So I'll go through each of these things that are labeled in the diagram and sort of explain where they're coming from. So first of all, if we have this half edge and we want to know the other half edge that's associated with the same edge but oriented in the opposite direction, we can call the opposite member function. So if I apply the opposite member function to H, this will give me the half edge that's oriented in the opposite direction from my original half edge H, which is this half edge here. So this would be H opposite. If we wanted to know the incident facet for this half edge H, we could call the H, or call the facet member function for H. The face or facet that's on the left-hand side of this half edge H is this face here, this triangle facet. So this corresponds to H facet. And then this particular facet on the left of H, in other words, the incident facet, it has 3 half edges that are incident on it. This half edge here, and then this half edge here. And what the next and previous member functions do is return, if we go around all of these half edges that I've just marked previously in a counterclockwise direction, the next member function gives us the one that we encounter next after H. So as we're moving around in the counterclockwise direction, the next half edge we encounter along this incident face is this half edge here. So this half edge is H next. On the other hand, if we went in the opposite direction, instead of going counterclockwise, we go in the clockwise direction, the next half edge that we hit is H previous, or previous. If we wanted to find the right face, the face on the right-hand side of this half edge, what we would do is we would call opposite first to get the half edge that's oriented in the opposite direction, and then we would call the facet member function for H opposite, because the facet that's on the left-hand side of this half edge is the same as the facet that is on the right-hand side of this half edge. So if we call H opposite facet, that will give us this facet here, this triangle facet. Then if we focus on the functions that relate to incident vertices, we have this half edge H. If we call the member function vertex, this gives us the incident vertex for the half edge. So the incident vertex is the vertex at the terminal end of the half edge, which is this end here. So this corresponds to H vertex. Then we have member function next on vertex and prev on vertex for getting the next incident vertex and previous incident vertex in the clockwise order about this vertex H vertex. So if we call for the half edge H, if we call next on vertex, it will give us the next half edge in the clockwise direction after this half edge about this vertex here. So if we go in the clockwise direction, rotating about this vertex here, we're going to move from this half edge here to this half edge here. So the half edge that we end up with for next on vertex is this one that's indicated here. On the other hand, if we're sitting at this half edge here, at this half edge H, and we're interested in this vertex here, and we call the previous on vertex function, the function prev on vertex, it's going to give us the vertex that comes previous in clockwise order, or equivalently next in counterclockwise order, about this vertex. So if we rotate in the counterclockwise direction, the next half edge we'll encounter is this half edge here, indicated by this 0. So this is what's returned by prev on vertex for our half edge H. If we wanted to find the vertex which is at the originating end of this half edge, what we would do is we call the opposite member function to get the opposite half edge, and then we find the incident vertex for this opposite half edge, which would be this vertex here, which corresponds to H opposite vertex. So this is how we find the vertex at the originating end of this half edge. Stream inserters and stream extractors for the polyhedron 3 class are provided. In other words, the left shift and right shift operators are overloaded for performing I/O. And in particular, if you try to input or output a mesh using the stream inserter or stream extractor, this will either read or write Polygon mesh data in the OFF format. So this is quite convenient if you want to do I/O with meshes. Lastly, on this slide, I've listed some common pitfalls to be careful to avoid when using the polyhedron 3 class. The first is to be careful about operations on the polyhedron 3 class that may invalidate handles, iterators, or circulators. You have a similar sort of issue, for example, when you use the vector class from the standard library. If, for example, you call the pushback member function of the vector class in the standard library, the pushback member function has the potential to invalidate iterators and pointers to data inside the vector and references to data inside the vector and so on. You have similar sorts of issues with the polyhedron 3 class, so be careful about these issues. The next thing to be careful about is that there's two types of circulators for the polyhedron 3 class. You have half-edge around vertex circulators and then half-edge around facet circulators. And what's important to note about these circulators is they iterate in opposite directions. One of them uses counterclockwise direction, one uses clockwise direction. So in cases where you care about the order, and sometimes you will care about the order, be careful that you are iterating over things in the order that you expect. The next thing is be careful about const correctness in your code. And often a source of problems, sometimes leading to very cryptic sort of compiler error messages with respect to templates, is not using the right version of a handle or iterator or circulator. In other words, not getting the constness correct when you're trying to specify handle or iterator or circulator type. The next thing to watch out for is some polyhedron 3 operations are only valid if the border is normalized. Some examples of such functions are size of border half edges and size of border edges. There's a few other functions as well. These functions will only work correctly if the border is normalized. And then lastly, exactly one of two half edges associated with the border edge is a border half edge. Sometimes, for some reason, there's a misunderstanding that arises that both of the half edges associated with the border edge will be border half edges. This is not the case, and if you stop to think about the definition of what it means for a half edge to be a border half edge, this clearly doesn't make sense. But for some reason, this seems to be a common problem that people will sometimes run into. So be careful about this.